Okay, so now we understand Gaussian elimination, we understand the purposes of what we're trying to do. Let's go through an example of how to solve this using naive Gaussian elimination. Now, what I really advise you to do is to actually go along this at the same time as me. So in other words, have a bit of pen and paper out in front of you and actually write this stuff down and go through it at the same time as me. Because I'm going to be introducing some terminology along the way. So I advise you as you're going through to write down the terminology, write down the definition which I give you, and that will kind of help you to understand what's going on here. So with this example here, we've got three unknowns, x1, x2, and x3. Therefore, we've just seen that we need a minimum of 3 equations in order to solve that. So I've written down my minimum of 3 equations here. Now, we also need to make sure that when we're doing Gauss elimination, that the number of unknowns and the number of equations are the same. So if we have more equations, great, but you just need to pick 3 equations that you can solve here. So 3 unknowns, 3 equations, or in general, n equations means n unknowns, okay? Now, just thinking about the optimization and thinking about the efficiency of the algorithm, I know that with naive Gaussian elimination, that if there's n unknowns and n equations, I'm expecting n minus 1 steps in order to solve this. So in this case, there's 3 unknowns, 3 equations. I'm expecting 2 steps in order to solve this using naive Gaussian elimination. So, bit of work to do to make sure we're set up properly first. First of all, I need to make sure that I've written my system of linear equations down properly. So in other words, I need to look at the columns of my system. And I need to make sure that I have the same variable, the same unknown in each column of my system. So in other words, the first column is all x1s, second column is all x2s, third column is all x3s. And the idea is that I want to try and rewrite this system as a matrix representation. So first of all, let's have a look at the left-hand side. What I'm going to do, because I know that I'm set up correctly, so the columns are all x1s, x2s, x3s, they're all the same variable. What I'm going to do first of all is I'm going to write the coefficients of the x1s, x2s, and x3s as I see them. So for example, I'm going to take 2, 2, and 2, the 1, 3, and 4, and the 4, 3, and 6. So you can see here I am literally just pulling out the coefficients of the x1s, x2s, and x3s from each of my different equations. Okay, so I'm going to call this my coefficient matrix, and I'm just going to give it a letter, so I'm just going to call it A, okay? But I also need to make sure that I still get this system of linear equations back when I put it into a matrix representation, otherwise they're still identical. So what I'm going to do now is write down a vector of my unknowns. I'm going to write down x1, x2, and x3 as such. And just because it's all in terms of x, I'm just going to call this vector x, and it's a vector, so I'm underlining it. Now, it might be worth pausing the video for a couple of minutes and just making sure that you can convince yourself that that is exactly the same as the left-hand side here. So in other words, multiply these two things out. Convince yourself these two things are definitely the same. So pause the video now. Okay, so hopefully you've had the opportunity and you're now convinced that these two things are the same, so the left-hand side is the same. The only thing left to do is just to make sure that I keep the vector of known values, so the 6, the 8, the 13. So I'm just going to write that down on the right-hand side. I'm just going to give that a name, that's a vector, so I'm just going to call it vector B. So effectively what I've done is I've taken this system of linear equations and I've written it in matrix representation. So in other words, A times X is equal to B. Okay, fantastic. So now when it comes on to naive Gaussian elimination, I just need to work with the values. So I need to look at these two matrices and vectors and things which are going on here, and I need to just take out the values from this. So the values I'm going to take from my coefficient matrix, so the 2, 2, 2, 1, 3, 4, 4, 3, 6. And on the right hand side, if you want, you can separate this with a straight line just to make sure that you are definitely separating them. Don't have to though. I'm just going to put my known values, so the 6, the 8, the 13. So in other words, I'm just collapsing this down to the values that I know, okay? All right, fine. Now what I'm going to do is, using naive Gaussian elimination, I'm going to use something called Ford elimination. Now the idea of this is that I want to eliminate as many of the coefficients of my unknowns as possible, so that hopefully I could just then solve a simple system of linear equations in order to figure out what my values of x1, x2, and x3 are. So let's go through them in order. Let's first of all look at x1. Okay, so let's first of all look at x1. Now, are you happy that in this matrix that I formed on the left-hand side, the first column of that matrix is going to be the coefficients which correspond to x1? If you're not sure about that, just scroll up to our system, and are you happy the 2, 1, 4, they are the same. Okay, so I'm going to be looking at this particular column here first of all, and I'm going to start here. Now the idea is I want to keep one of the coefficients. So in this case, I'm going to keep the coefficient in the top row. Okay, so I'm going to keep that there. So I'm going to call this my pivot. So my pivot for x1 is going to be 2. And what I'm going to do is I'm going to try and get rid of this 1 and 4. So in other words, I'm going to try and make those coefficients go to 0 by adding and subtracting multiples of that first row from the second and third column. Okay, so let me show you what I mean. Let's first of all consider row 2. So I'm just going to write row 2 here, or R2 for short. So in other words, I'm going to look at row 2 and I want to try and get rid of this 1 from my matrix. In other words, I want to try and make it go to 0. So first things first, I need to figure out what the multiplier is. So how many times I'm going to add and subtract row 1 from row 2 in order to eliminate that 1 and make it go to 0. Now in order to work out what the multiplier is, I just simply take the element which I'm trying to get rid of, which in this case is 1, and divide it by my pivot, which I just said was 2, because it's the first row, that's the thing which I'm keeping. Okay. So therefore, if I just take row 2 and subtract my multiplier, which is a half, from lots of row 1 from row 2, then I should end up with that element which I'm after, that 1, that should go to 0. Okay, so let's check that out. In fact, let me make a copy of this diagram down here, or this matrix down here. So there we go. And I'm just going to get rid of this row and this row here. So let's write down my new row in the next row 2. Okay, so in other words, what I'm going to do is I'm going to take all of the elements in row 2. So I'm going to take this 1, and I'm going to take away a half of whatever the corresponding element is in row 1. So in other words, I'm going to take the 1 and I'm going to take away a half of 2. Well, 1 take away a half of 2, that's going to give me 0, as expected. But I need to do it for all of the elements. So let's move across. For the next one, let's take 3, and I need to take away a half of 2. So 3 take away a half of 2, that's 3 take away 1. That is going to give me 2. And if I move across to the next one, so the next element would be 4, and I need to take away a half of 2. So 4 take away a half of 2, that's going to give me 3. And then if I move across to the final one, which is the 8, so I need to take 8 and take away a half of 6. So 8 take away a half of 6 is going to give me 5. Now you can see that that's exactly what I wanted, okay? Because this element, the element corresponding to the coefficient of x2, I've reduced down to 0, okay? Now let's do the same thing, but for row 3. Okay, so let's move on to row 3. So in this case, I want to change 4 to 0. So if we do row 3 down here, so R3 for short, let's first of all figure out what the multiplier is. Okay, so the multiplier, remember, is the element which I want to get rid of, in this case 4, and I want to divide by the pivot, so in this case 2. Okay, now 4 divided by 2, hopefully you're happy, that's just equal to 2. So in other words, I can say that in order to get rid of that element, make it go to 0, I can say I need to take row 3, and I need to take away 2 lots, that's my multiplier, of row 1. That's my pivotal equation. That's the equation which I'm adding or subtracting multiples of. Okay, so let's figure that out. So row 3, well okay, I'm going to take my 4, and I'm going to take away 2 lots of row 1. So I'm going to take away 2 lots of 2, that's going to give me 0, as expected. Okay, now that's always a good check to do. If you don't get 0 there, you know you've done something wrong. Okay, now let's move across. Let's move across to the next element, which is 3, and I'm going to take away 2 lots of row 1, so that's 3 take away 4, that's going to give me -1. And if I move across to the next element, which is 6, and take away 2 lots of 2, that's going to be 6 take away 4, that's going to give me 2. And if I move across the final element, that's going to be 13. And if I take away 4 lots of 6, that's 13, take away 24, that is going to be equal to... Sorry, my mistake there. It should be 13 take away 2 lots of 6. That's 13 take away 12, which is just going to give me 1 there as expected, okay? So this is basically the end of the first step. The idea is that I'm just left with one coefficient of x1 in my first column. So that's step 1, okay? Let's move on to step 2, and I'm going to try and do a similar thing for the coefficients of x2. Okay, so same thing as before. I need to figure out what my pivot is going to be. So my pivot in this case is going to be related to x2. And I don't really want to adapt row 1 because that was all to do with the pivotal equation of x1, my first unknown. So all I do is just look at the next row down and I say, okay, the second row and second column, that is the coefficient that corresponds to x2. And I don't want to adapt the first equation, which is why I'm not using that one. So I'm going to use the second equation instead. Okay. So in other words, I know that my pivot is going to be 2 in this case. It's a second row and second column. And I just do a similar kind of thing as before. So the idea is I don't want to change the first row anymore because that is what I want, okay? I just want to go to the third row and I just want to try and get rid of this -1, okay? So this is the second step of my Ford elimination. All right, so let's first of all work out what my multiplier is. So looking at row 3, let's figure out what my multiplier is. Now just remember, the way which I work out my multiplier is exactly the same as before. I want to get rid of this -1, which means that I need to take the -1 and I need to divide it by my pivot. So this is going to be -1/2. In other words, in order to get rid of this element here, the -1 in row 3, I need to take row 3 and take away a half, or -1/2, of row 2. Okay, so that's how I get rid of the element in row 3. Now, of course, take away a negative, that's just exactly the same as a positive. Okay, so let's figure that out. Let's actually start off by writing down a copy of this matrix. I know that my third row is going to change, so I'll just put some spaces in there. All right, so let's go through in order. Let's do it properly. So in other words, I'm going to start off with 0, and I'm going to add on a half of the element in row 2. So in other words, 0 plus a half of 0, that is still 0. That's good. I don't want that to change because remember that's the element of the coefficient corresponding to x1. Now let's move across and let's go for this one. So -1, add a half of 2. Well, -1, add a half of 2, that is going to give me 0, which is exactly what I want. So again, use that as a check. Make sure that your element which you want goes to 0. But let's move across because of course we need to do it for all. So 2 plus a half of 3, well, that's going to be equal to 7/2. So let's fill that in, so 7/2. And let's move across to the last one, which will be 1 plus a half of 5. So 1 plus a half of 5 is going to give me 7/2 again. Okay. Okay, so in other words, this is the matrix which I formed at the end of my second step of Ford elimination. Now, if you remember right at the very beginning that the number of steps of Ford elimination was always n-1. So in this case, we had 3 unknowns, and I was expecting to do 2 steps. This is what I get at the end of my second step, and I think this is exactly what I want. Now, just be aware here, we can give a bit of terminology. We call this an upper triangular matrix. So we call the 2, 2, 2, 0, 2, 3, 0, 0, 7/2. That matrix there is what's known as an upper triangular matrix. The reason being is because there's no elements down here. The elements down here are gone. In other words, there's only elements in the top. Okay, so in the top sort of right portion of my matrix. This is an upper triangular matrix. Okay, and this is what I want. You might sit there thinking, well, okay, how does that get me any closer to solving these equations? But actually, it's exactly what I want because I understand how these things are constructed. Okay. The reason being is because my first row was all to do with x1, the second row was all to do with x2, and the third row was all to do with x3. So this row was x1, this row was all to do with finding x2, and this row is all to do with finding x3. So now I can do the next kind of process of naive Gaussian elimination, which is something called back substitution. Now, the reason why it's called back substitution is because I now go back and substitute values in to make sure that I get the values of x1 and x2 which I want. And it's also called back substitution because I'm going backwards. In other words, I'm going to start at x3 because that's the easiest one to solve. Then I can go back and figure out what x2 and x1 is equal to. So, okay, let's figure out x3 first of all. So I know that x3 should basically be using the final equation here. So in other words, when I multiply what my matrix representation is out, I should end up with 7/2 times x3 should be equal to 7/2. Hopefully you can realize where I'm getting those numbers from. I'm literally just taking this element because all of the other elements, in other words, the elements corresponding or the coefficients corresponding to x1 and x2 are 0. So therefore I can just read off that 7/2 x3 should be equal to 7/2. So therefore if I solve that equation, are you happy that I can say that x3 should just be equal to 1? So in other words, I found the value of x3. Now I go back, and using the value of x3, I can go back into the second equation to find x2. So x2, I can use my second row, so I can use this row here. And I can say, well, okay, I haven't got a coefficient of x1, but I have got a coefficient of x2, so I can say 2 lots of x2 plus 3 lots of x1 should be equal to 5, okay? So now I know what the value of x1 is. I can just replace this in here, so I can say 3 times 1. And if I solve this, I find that x2 should be equal to just 1 again. So x2 is equal to 1. Okay, cool. And now I go back again to x1, so right back to the very start, so x1. And now I use that top equation, so in other words I use the top row of my matrix, and I can just read off the coefficients. So 2x1 plus 2x2 plus 2x3 should be equal to 6. So 2x1 plus 2x2 plus 2x3 should equal 6. Now clearly I know the value of x2, that's equal to 1. I know the value of x3, that's also equal to 1. So therefore, I'm able to write that, x1 should just be equal to 1. Okay, fantastic. So in other words, that's how I'm going to solve my system of linear equations using Gaussian elimination. Let's just make sure we're happy, okay? So the first step is to make sure that our system of linear equations is written correctly. In other words, that the columns match up with the unknowns. So the first column is x1s, second column is x2s, third column is x3s, etc. Okay, then I can convert this into a matrix representation of my system of linear equations. I then use forward elimination, and the idea is that I figure out what my pivot is. So the idea is the first row should correspond to x1, my first unknown. That should stay the same, and I use the first column to represent my pivot. I then work out what my multiplier of my second and third row is. That's just basically by figuring out what element I want to get rid of and dividing it by the pivot. And that's how many times I subtract row 1 from either row 2 or row 3. Then the second step, I just go through and just repeat exactly the same idea, but of course I'm working down, so I'm now doing x2. And the idea is I want to get rid of this element here, I want to make that go to 0. So again, I just figure out what my pivot is, so it's the second row, second column. Work out what my multiplier is by dividing the thing which I want to get rid of, in other words the coefficient of my x2, divided by my pivot, and that's how many times I subtract row 2 from row 3. And then I can just read off directly from my upper triangular matrix by using back substitution what x3, x2, then x1 is equal to. Okay? So just a little bit of terminology which we've met along the way. We've used things like pivotal equation. Remember, the pivotal equation is basically the equation that stays the same at each step. So for example, the pivotal equation in this case when I was looking for x1 was the first equation. The pivotal equation for x2 when I was solving for x2 was row 2. Okay? The pivot, which was basically the thing that we were working out the multipliers from, and then we were also using forward substitution, back substitution. Of course, an upper triangular matrix is basically a matrix of this form, where the idea is that the lower part is just zeros, and we just have numbers in the upper part as well. So in other words, the numbers above the diagonal, so the top right of the diagonal, okay? So in the next videos, we're going to be looking at ways in which we can make things more efficient.